All right, we're going to talk about Earth's magnetic field. So here we've got our Earth, and inside of this, we'll put the inner core, and then we're going to dash this line. It's not going to be a perfect circle, outer core. Okay. Then we've got the mantle, right, and we've got the crust. Great. So inner core, this is the outer core. Okay. What you need to know about is the outer core here is a liquid. The outer core is constantly moving around. Okay. The inner core, it's like sloshing around. It's not always going in the same direction. Sometimes it's going in different directions. What's happening as that outer core is moving around, or as the liquid outer core is moving around the inner core, it's generating a field. The field that it generates is a magnetic field. Okay. So I'm going to draw that kind of like if this were an apple, and we're going to make, you'll see these lines that leave from either side. These lines are representing the direction and the strength of the field. So the core is moving, it's generating this magnetic field, okay? And this thing is three-dimensional, so it's like a big circle around the Earth as well, okay? So we're getting this magnetic field that comes out of one pole and goes into the other. So this will be your North Pole, this will be your South Pole. You guys have heard about the poles, right? So on a magnet, the North Pole and the South Pole are just opposite polarities. They have opposite magnetic kind of abilities or attractive forces or what have you. So you know that if you've got a north and a north, they repel, and a north and a south, and they come together. So opposites attract, that kind of thing. Okay, so here's our magnetic field. This magnetic field is stopping things like radiation in form of solar wind from coming from like the sun and stuff and just coming straight to Earth. Instead, this magnetic field is kind of deflecting those objects out. So they'll come in and they'll deflect away. Okay, so the magnetic field kind of keeps us safe from the solar winds here on Earth. This doesn't exist on somewhere like Mars, which is why the surface of Mars is like a big desert. It's been kind of bombarded by these particles for a long period of time. So that's kind of part one. The next thing that you need to know about is the polarity is actually flipping. So let's bring this picture back in here, okay? So sometimes what we consider the North Pole and what we consider the South Pole, they'll flip. Now the Earth doesn't actually turn, just like the polarity changes, okay? And as that polarity changes, it would basically make your compass point the opposite direction. Now that hasn't happened in human existence because we haven't been around for a very long time, but every few hundred million years, something like this might occur where the poles flip. And where that's recorded is in the rocks that make up the Mid-Atlantic Ridge. So if we put the, let's just take a second to zoom out. I'm doing this with my hand, sorry. There we go. If we go like this, so we make a ridge. This is the Mid-Atlantic Ridge, okay? So we've got crust is opening up, and we're forming new crust here in the middle, and it's pushing the old crust out. So new stuff is forming here, old stuff is pushing in this direction on both sides, right? Okay? So what we know is that this new lava that cools and hardens to make brand new crust, it records the magnetic field of the Earth on the day that it forms, okay? So what happens is you've got this liquid, right? And it's like a liquid molten rock, and when it comes out and cools and hardens, it's got these little magnetic bits in it. So let me draw you a diagram. Okay, so here is an object, and it has these magnetic regions in it. So we'll split it up randomly like this. Okay, so all these little squiggles represent a magnetic region, and they all have particles in them. And some of these particles are things like iron that are kind of magnetic and stuff. And when you've got something like this, the direction that I'm pointing with these arrows to would be like the direction of magnetic north, okay? So here is an object that is not magnetic because all of the little regions have little pieces of iron that are pointing any which way, okay? So this object was not in a magnetic field when it cooled into a rock. But if you get a rock that has these regions in it, I'm gonna do less regions just because I'm gonna need to do that for time purposes, so we're gonna do fewer regions. Let's do it this way. Try and make it a little bit more structured, but also less structured. Okay, so in this case, if you expose something like this while it's in its cooled form, so the particles can still move around, because once you've hardened into a rock, the particles, they're not going anywhere unless you can melt it down again, right? So when you've got this molten rock, like that's coming out of the spreading center here where the seafloor is spreading, this molten rock, right? Molten, okay? If we take this molten rock and then we put it in Earth's magnetic field, which it will be in when it starts to come out. So when the rock comes out of the center here, it's molten, it's gonna start forming up And before it hardens, the iron bits are going to point in the direction of the magnetic North Pole. So if the magnetic North Pole is actually up, and all the little bits start to point up, oh, that's supposed to be an arrow, man. Whew. All the little bits are pointing up. There you go. See how all the bits are aligned? Since all the little fragments, all the sections are aligned, this whole thing is basically now a small, crappy magnet. It's a weak magnet. And it's saying that north is that way. Okay? So this thing will actually kind of affect a compass or anything that measures magnetism. So this is kind of what's happening in our seafloor spreading when this new stuff comes in. So what happens here is, as this new crust comes out, it's going to create a band of that crust right on either side. Okay? And that band is freezing in time, which direction is magnetic north. So let's say that in this case, magnetic north is this way, right? So that's what happens now. Okay? Now, if you go back to the previous iteration, the previous point where there was crust forming, that would be the stuff that's just a little bit older, right? So let's call this 1. So this is 1, and these are 2s, right? And I'm going to dash the 2s so that you can understand that they're different. Sorry, this is tough to do. I should have got a third hand in here to help me out, you know? Should have gotten somebody to help me. Okay, so you can see the 1s and the 2s are different, right? So the 2s, they're older. They may have been in the last magnetic reversal, so they might have an arrow that's saying that north is actually down, right? Which, like, that would be totally weird for you and me because we know that south is down, but, or well, south is is the bottom of Earth, but really we don't know. We just are experiencing the magnetic poles that we're experiencing now. So what we found when we went down and looked at the bottom of the sea was that sometimes our magnetic readings are saying like, oh, up is north, down is north, up is north, down is north as you go back. So you can actually record this for like the past 180 million years by going through this area and just checking with a magnet or a magnometer, something that measures magnetic fields. So this is going to help you with that section that says, if you don't know this or you need help, go and look at the video that says Earth's magnetic field. That's it.